Hi everybody. We're going to take a look at the direct comparison test for convergence as well as the limit comparison test for convergence and develop those concepts. And in the other video, we go through a few examples, okay? So let's take a look first at the direct comparison test. So suppose we have this series here as n goes from 1 to infinity of 1 over n squared plus 1, and we want to see if that converges or diverges. Right, well, if you look at it, it's not too unlike 1 over n squared, which we know is a convergent p-series. The only difference is we have that plus 1 in the denominator. If you think about it, as n gets bigger and bigger and bigger, that plus 1 isn't going to make too much of a difference. All right, so if 1 over n squared converges, intuitively we might be thinking that this will as well, because it's really not too different, right? In fact, let's take a look at the first few terms here. If I plug 1 in, let's see, we get 1 over 2. Plugging in 2, we're going to get 1 over 5. Plugging in 3, 1 over 10. And 1 over 17, dot, dot, dot. All right, so let's compare that to 1 over n squared. Okay, we know that's going to be 1 over 1, 1 over 4, 1 over 9, 1 over 16, so on and so forth. Okay, now again, we know that this is a convergent p-series. Okay, compare now term for term what's going on. Notice that in each case, the terms in our original series have a larger denominator. Well, what does that mean about the value of that fraction? Well, it means it's smaller, right? So the darker blue terms are smaller than the lighter blue terms here, term for term. The first term of this is smaller than that. The second term is smaller than that second term. Third term is smaller than that third term, so on and so forth. Okay, so the corresponding terms in our given series are less than those of this convergent p-series. Well, what does that mean? Well, if these terms that are larger converge, and we know that these guys are going to be smaller in value, then by comparison, we can make the claim that this guy is also going to have to converge. Right? And that's the idea behind the direct comparison test. Okay, if we can show basically here that this is less than or equal than that, and we know that this guy already converges, well then by the direct comparison test, this one's going to converge as well. Okay, so let's take a look at the next example, and then we'll kind of formalize it here. All right, in the next one, we have the summation as n goes from 1 to infinity of 2 over n. Okay, and it's 2 over 1, 2 over 2, 2 over 3, 2 over 4, etc. Okay, now those terms do approach 0. But this thing, again, doesn't look too much unlike the harmonic series 1 over n. And we know that this diverges. Okay, well again, let's compare term for term. Well, the first term of this divergent series is 1. The first term of our series is 2. Here we have a half, there we have 1. Here we have a third, there we have 2/3. 1/4, 2/4. Seems as though that the original series 2 over n, term for term, they're larger than the terms of this divergent harmonic series. Okay, so what do we know? Well, if the harmonic diverges and all the terms of this are going to be greater than the corresponding terms of this one, then this guy is going to have to diverge as well. Okay, and again, that's the gist of the comparison tests. We take our given series, we compare it to something we're familiar with, and if we can show a certain type of comparison, a certain type of inequality, hey, look, all the terms of our series are less than the terms of this convergent one, then it's going to have to add up to something smaller, and it's going to have to converge as well. On the other hand, if we can show a given series is larger than a series we know already diverges, then those terms are just going to add up bigger than a series we know that already goes to infinity, and so that's going to have to diverge as well. Okay? So the comparison test. Suppose we have two series. And we will call them summation of A sub n and B sub n. Okay, so we're adding up all the terms. In some sequence we're calling A, and some sequence we're calling B. Okay, so we have these two series, and important, the terms all need to be positive. A sub n greater than 0, terms in B sub n all greater than 0. Okay, and also, let's define the terms in the A series to be less than or equal to corresponding terms in the B series, okay? So A will be the smaller, B will be the larger, okay? Then, okay, if the larger series is convergent, then so is the smaller, okay? If B sub n is a larger series, like the 1 over n squared, and that converges, and we can show this A series is less than that, then we know the A series is going to converge as well, okay? And then also, if the smaller series is divergent, well then, so is the larger, okay? Now, what we have to be careful of is the order of this matters, okay? If the larger converges, so does the smaller. If the smaller diverges, so does the larger, okay? Just because the smaller converges, it does not mean the larger will converge. So we will have to be careful, all right? And also, just because the larger diverges, it does not mean the smaller will diverge. Okay? If something goes off to infinity and we can show that these terms are less than that, it might still go to infinity, but it might not, okay? So the order matters. If the larger converges, so does the smaller. If the smaller diverges, then so does the larger, okay? And again, relatively intuitive here, okay? Now, sometimes we're going to run into a situation where we won't be able to determine an inequality when we're trying to use the comparison test, as you'll see in the examples in the other video. Or we'll be able to come up with an inequality, but it'll be more like one I've written in red, okay? Like, oh, we showed the smaller one converges, but we don't know necessarily what this one that we were given that ends up being larger does, okay? So we have this other test called the limit comparison test that can help us out. And so the limit comparison test for convergence says the following. Suppose, again, we have two series. And again, we're going to call them A sub n and B sub n. Here, all that matters is that all the terms are greater than 0. Doesn't really matter which one is larger in this case, okay? It doesn't matter if A is the smaller, B is the larger. Not going to matter here. What we're going to do is we're going to let C equal the limit as n goes to infinity of A sub n over B sub n. Basically, what we're going to do is we're going to see if the ratio of these series we have approaches some number as n goes to infinity. Okay, the terms of the sequence, okay, approaches some number. It doesn't really matter which way you set this up. You could also set it up like this. Okay, it doesn't matter which way we set that up. All right, but here's the outcome. If that limit, that number C, is a positive finite number, okay, basically it's some number between 0 and infinity. It's got to come back positive. It doesn't matter what it equals as long as it equals some number. It just can't go off to infinity, okay? Then either both series converge or both series diverge. Basically, both series will do the same thing. Okay, so here's what's going on. Okay, kind of like the proof of this thing, if you will. So, because C is some number, C equals this limit. Okay, try again to think about what's going on. We have two series. We're gonna go off to infinity with both, and we're gonna look at what happens. Like, what does the A series approach? What do those terms approach, and what do the B series terms approach? Okay, and then we're gonna take the limit as n goes to infinity and divide those things. Okay, and we're gonna call that number C. So suppose we have some number C that equals this. Okay, well then that means that C is some number on the interval 0 infinity. And that just means that, we could find two other numbers, one smaller and one larger than C. We're going to call them little m and capital M. Okay? So whatever C is, some positive number, we can find two numbers that surround it, little m and big N. That's all we're going to say. Now, since C is equal to the limit as n approaches infinity of this ratio, at some point, that ratio itself is going to approximate or approach the value of C. So I'm going to sub that in for C. Okay, and now what we're going to do is we're going to multiply through by b sub n. Let's get that out of the denominator. So we're going to have little m times b sub n less than the series given by a sub n less than capital M times b sub n. And again, little m is just some number that was smaller than c. Capital M was some number that was bigger. Okay, and we replace c with this ratio, a sub n or b sub n, because that's where c comes from, is looking at what that approaches as n goes to infinity, and then we multiplied the b sub n out of the denominator. Well, now what we can actually do is use the results of the comparison test that we just talked about above to make sense of the outcome here, that if this limit equals some positive number, that both series will do the same thing. Think about it. If b sub n diverges, then so does the series given by m times b sub n. A multiple of a divergent series is divergent. Well, then by comparison, since a sub n is larger than that, this will also have to diverge. Okay? So there's the idea there. Now on the other end of things, right, if b sub n converges, then so does the series given by capital M times b sub n, because a multiple of a convergent series converges, right? If something adds up to, say, 1, and we multiply that by 5 halves, well, then that's going to add up to 5 halves. That's all, right? So again, though, now we say, well, look, since a sub n is less than this series, okay, whoops, I misspoke. I meant to say if b sub n diverges up here. Okay, so does the bigger one. No, I messed up again. Converges. Okay, if the larger one converges, right, so does the multiple of that. I said it correct the first time, and then I made a mistake. Sorry about that. If the larger one converges, okay, then so will a sub n, because it's smaller than that. Okay, so that's the gist of the limit comparison test. Okay, so your job ultimately, though, is going to be, if you look at a problem, does it look similar to something we're already familiar with, like a p-series or a geometric series or a harmonic, something along those lines, and we'll set up a basis of comparison, and we'll see if the direct comparison test tells us anything, and if that's inconclusive, we run the limit comparison test. Okay, so check out the next video. I go through a bunch of examples in that, and it'll probably make a little more sense then. All right, but hopefully this helps you with the idea, the concept, and we'll talk next time. See you guys.